All right, so what do we know about springs so far? We know Hooke's law. F is equal to negative kx. There's more to it than just that. Let's think conceptually for a second here. We have this spring right here. Is there any energy in this spring? No, not at all. There's no energy in here. Now, if I do this, what did I just do to the spring? That's right, I added energy in the form of work, right? I did some work to the spring. It moved. I applied a force over a certain distance. It moved. Now there is energy in the spring. What about if I close it in? The same idea. Yeah, the spring, with some force applied to it on a certain distance, is going to feel energy. It's going to have energy transported into it. And we can graph it like this. Let's say we got our y-axis and our x-axis. So our x-axis we'll say is how far the spring moved from its resting position. And for our y-axis we'll say, okay, this is the force. Now, if we apply some force right there and it goes to some certain distance, we say, all right, there, and then there. It will line up right there, and we get this line. Right here. That's our line. What does this line represent? That is our K. That is our spring constant. That is our stiffness. Does that make sense? When you apply some force to it, it only goes some certain distance. That is your K. That is your spring constant. That is how stiff it is. Now the question remains, how much work, how much energy did you put into the spring? Well, we look here. Is it this whole box? No, it's not. It's just this portion. You should know this from geometry. It's basically the area of this triangle. And we know the area of the triangle, the area is equal to 1/2 base times height. So if we just put it here, our area is actually the work that we did on our spring. So we say, okay, the work we did is 1/2 our base times our height. I'm just going to write it like this, 1/2 Fx. What else do we know? We know that F is equal to negative Kx. So if we take this and plug it in right here, we actually get that work is equal to 1/2 Kx squared. And this negative, remember, is just basically there to say that the spring does the opposite of whatever you do to it. So our work is equal to negative 1/2 Kx squared. It looks a lot like the kinetic energy formula, I know, but it's just different. It's saying that work you did is equal to 1/2 times the spring constant, how stiff it is, multiplied by the distance it changes squared. I'm going to show you this. The potential energy of a spring is equal to negative 1/2 Kx squared. They are the same. Why are they the same? They're the same because at its initial resting point, when you do nothing to it, it has no potential energy. It's not like an object where we can just set it on something and say, okay, that has potential energy. No. This spring, you need to do work to it to give it energy, to give it potential energy. So the same amount of work that I do to pull it out like this is the same potential energy that this spring has. So using these two equations right here, and really these three equations right here, go ahead and try this worksheet. I think you guys will be really good at it.